So today we'll continue talking about policy gradient theorem, or different interesting topics about policy gradient. So to ground us up a little bit to the topics we already covered, we've been talking a lot about reinforcement learning, right? So many topics in reinforcement learning or the design of different algorithms around playing with these different objects, right? So one object is a policy, that the thing you really care about at the end of the day. You want to have some decision-making policy you roll out to, venture into the world and make decisions. And also the value functions, which get you different basic principles of how to optimize a policy, like invoking the Bellman equations or the Bellman optimality equations and so on, right? So some of the basic ideas, including policy iteration, involves simulating some interaction between these two objects, right? So in policy iteration, you're used to the idea that you have some existing policy that's not very good, you would like to improve it. The first thing you want to do is do some kind of policy evaluation. And that usually means you write down a bunch of value functions, evaluating how good a policy is at different states for taking different actions. And as soon as you write down these value functions, it basically provides different ways to immediately improve the policy, right? So one basic way to do that is to just stare at the Bellman optimality equations that allow you to do some sort of greedy update. And in Drew's lecture, it's basically, he told us something other than a greedy update, which is, you might want something more conservative, like a conservative policy iteration. Right, so we won't repeat a lot of these things today, but that was sort of the mental picture before the last lecture. So what's policy gradient going to do? Well, it sort of takes in the perspective of whether we can slightly abandon this picture for now and do direct optimization here. So can we temporarily depart from this loop and think about whether there's like a more direct optimization technique on the policy? Because the policy is, at the end of the day, usually is the thing you really care about, right? So you want to make decisions. And why is that, right? Why do you sometimes want to depart from this? Well, there are problems you can write down where it is easier to optimize the policy directly than to learn a comprehensive set of value functions that capture how well the policy is doing. Okay? So you can start thinking about what these examples might look like. But one example that is very close to our life right now is language models, right? So in a lot of the applications to language models using RL, such as RHF, it's usually unrealistic to, or not necessary to compute all the intermediate state or action value functions. A lot of the algorithms actually operate essentially by direct optimization, so doing some kind of policy gradient optimization on the policy. Okay. So there are problems in which you might just think about whether you can throw modern optimization technique like gradient-based optimization at the policy. Right? So we'll get into some of the details later, but basically, you want to improve the so-called objective function by policy gradient ascent. I think ascend with the D is the climbing gym. Yeah, anyway. Gradient ascent usually end with T, I believe. So that usually means you add in some gradient that the total reward function pointing you to, right? So the total reward function give you some local improvement, some direction to at least provide some local improvement. In practice, this J of pi is almost always non-convex. So you have to get used to the idea that you may not get to a global optimum, but in real life, it seemed to work so quite well. And there's a little bit of detail from last lecture. Like in order to do that, you kind of need to make sure J is differentiable or at least continuous. So there's some parameterization of what the policy look like. So you're basically attaching parameters like some sort of vector to define what the policy, how the policy is making decisions. So usually it involves making soft max type of decision. You're kind of making inducing some sort of probability distribution of the actions, and the probability is nice, continuous, and real value. And that allows you to do some sort of gradient-based optimization. Okay. So we'll continue this roadmap. So there are a couple of things we want to do today. One, I want to state the policy gradient theorem in full. So we already saw part of it. And one issue we haven't talked about so far is you almost never actually observe the full gradient. In most of the problem you encounter, you have to estimate this quantity. Okay. So this is something we hinted at when we tried to derive what the gradient looked like. So this lecture we're actually getting to some issue around how you may, what are good ideas for getting a good estimate for these gradients. Okay. And the first idea people think of, usually called the Monte Carlo estimation, or Monte Carlo sampling, tend to have pretty high variance. Sort of the first idea you think of tend to have pretty high variance, and luckily the policy gradient theorem, like the variation of how to write down the policy gradients, allows you some interesting technique to reduce the variance by introducing some sort of baseline. Okay, so far we basically start with this picture where let's slightly abandon the value function for now. Let's just think about how to do gradient-based optimization. That's the thing we really care about. We want to solve RL, we want to optimize total reward. You can do that because you can write down the policy gradient by ensuring some sort of continuity in the parameters to the total reward. And then you start getting into some more practical issues, like how do you actually estimate gradients? You can mathematically derive it, but you can only get at it by rolling out a policy and learn and collect experiences from the environment. Okay, and the idea of variance reduction usually means you're actually subtracting some quantity from the typical, the basic estimator. It turns out usually the most common choice of what baseline means is the value function. Okay, so this actually leads to, by pushing this variance reduction ideas further, you actually get to what people like to call the actor critic method, okay, which is a little interesting in this landscape because what's actor critic? Well, basically it's bringing back the value function into the picture again, right? So we would like to use value function as a baseline. I will tell you what baseline means really, to reduce variance so that I get better estimate for the gradient. Okay, so the start of this picture is let's abandon the value function and not do something like policy iteration and do what we know modern machine learning is very good at, gradient-based optimization like SGD. It turns out a lot of the more practical methods that involve reducing variance bring back the values again. And it's sometimes called active credit method because the actor usually correspond to the policy. Obviously, you're using a policy to act in the environment, in the real world. The critic is sort of some object or some function that's evaluating the actor, and that's naturally the value function. So really it's just a different naming of this picture of how policy and value interact. And the value function is brought back in an interesting way, mostly with the motivation of reducing variance. And we'll spend a little bit of time talking about a sort of like a generalization of active credit methods called generalized advantage estimation. Hopefully we have enough time to talk about that. Okay, so that's the plan for today. Any questions so far? Oh, I did something dumb. Ah, never mind. I'll cover this. Okay, so there's a little bit of notations. Right, so we want to think about solving RL. Every policy will be parameterized by some parameter theta. This is something you have seen from last lecture. You would use the policy to interact in the real world with the environment, and you can almost think about the policy as a way to generate trajectories. And in language model, it really makes sense. Like your policy is like a transformer that should generate token, and token forms sentences and paragraphs and articles. But in general, you can think about once you pick some parameter theta, it defines a policy. The policy will go out in the real world and take certain actions. It will generate a history or trajectory like this. We're going to use tau as a notation. And again, to keep things consistent, we'll think about this finite horizon setting. Drew liked to use capital T for horizon length, but sometimes for me, I like to use H. And you just want to maximize the total reward. Okay, nothing interesting going on here, just notations. Like you just the object you usually care to optimize is the total reward. So capital R over tau. Okay, so where we stop at from last lecture is basically the policy gradient theorem, and we basically proved this version of it. So this is the J is again the objective value, the expected total reward. If you are at some policy with some parameter theta, what does the gradient look like? The gradient turned out to be somewhat simple, and it's just at the end of the day, you're just taking gradient with respect to the log likelihood of each action, of the taken action at each step. So everything is random here. This is like taking randomness over the trajectory. So you can imagine there's some distribution over SH and AH at every time step H. And you're taking expectation. So when you roll out a trajectory, you see some SH and AH at every time step. This will be evaluated with some log likelihood here. Okay, so there's a theta here, I forgot. And this is a function that depends on theta, so you can take gradient with respect to theta. So this objective is sort of taking the gradient with respect to the maximum likelihood objective people like to think about, and you just multiply with the total reward at the end. Okay. Let me clean this up a little bit. So this algorithm, or this form of the gradient, when you use this form of the gradient or estimate this sort of object, the algorithm usually is called reinforce. Okay. Remember to use all caps. So it's I try to use indoor voice, but like when you think about it, you should yell because it's all capital. So you can shout it out. Gokul was sending me a paper from an AI company recently They did a broad set of experiments on language models on how to optimize language models. You know, if you know a little bit about RHF, like an algorithm that we will talk about next week is called PPO, Proximal Policy Optimization. That almost became the go-to method for doing RHF. But that paper, interestingly, did a lot of comparison with reinforce, which is like the first policy gradient method you write down. It turns out this is, according to their experiments, as good as PPO and often do better, which is interesting. But you can see why for that kind of problem, like RHF, this is like a somewhat favorable method in the sense that like when you're doing language generation in RHF, like you learn a reward function from some preference data. It's not going to assign individual reward to every single token. How do you do that? It's very hard. The reward function is usually over trajectory. So the kind of object you learn from preference data is exactly like this. So it's on total reject, the entire sequence. So that's the thing you get signal for. And reinforce is somewhat designed for that kind of problem, where you only get a total reward signal at the end of it. Anyway, we'll talk more about this issue later. So there are actually 3 variations of this. The third variation you have already seen, which is the advantage version. We'll get to that in a bit. There is another version that involves the action value functions. I will try not to prove it, but state some intuition. So some observations. Okay, so what is this product really doing? Okay, so I'm gonna just write it out with slight simplification of notation. Okay, so what is the total? What's capital R's total reward? So this is again another summation here. Okay, so nothing interesting going on right now. Let's break this down a little bit. So this is enumeration over H, time step H. There's also an enumeration over H here. So just so far just copy and paste. I just want to break this sum down into 2 parts. So at time step H, so this is enumerating H. So like at time step H, there's stuff that already happened, which is like all the rewards I have already seen, and the rewards I am experiencing right now until the end. So all the rewards I have the immediate reward I have right now, and also all the future rewards. Okay. What is this object? What's the second term here? Future rewards. All the future rewards. So in the expectation, what would that be? I take expectation over randomness.
The value.
The value. Okay. What value?
BASH.
Ah, excellent. Good. So another way to write this is you can write the V as well. I'm gonna write the action value version. Okay, so this is like, you know, in this expression, there's an expectation outside I'm omitting. Like in this case, I happen to take the action SH and AH. You know, the randomly supply will lead me to take this action. So at this step, I will take AH, and then I will follow the policy to take further rewards. That's all the future rewards. Okay, so that usually if you take expectation, will come down to this Q function, Q value. Okay. All right, so nothing super interesting going on, but what about this? This feels a little strange. Hey, so what is gradient optimization trying to do? You can almost think about this as, right, like intuitively you're pushing up the probability on action that lead to higher rewards. At this point, you want to push up the probability for AH, some AH, that give you better current reward and future, because what happened in the past cannot be changed. Right? So if I look at just time step H, when I take the gradient, I should not expect the decision I make, like all the local improvement I make for this probability to affect the past reward. So this one, you can sort of pretend that, by updating through the gradient, by changing things on the parameter space theta, you should not be able to affect that. Okay? So it turns out that if you work out the mathematics, this product will be 0. So this is usually the causal interpretation of this product when there are things that you cannot affect it, like the gradient multiplied by this unaffected term with the expectation outside will be 0. Okay. So that sort of give you a sense of a second version of the policy gradient theorem, which essentially just remove the unaffected part of the total reward at every time step. Okay. Just enough space. Okay. So let's not prove it because it might be in the homework. The takeaway is that you should expect when you take expectation outside, this term should go to 0. Any questions so far? So this is only a slight change of format. Before, right, like, comparing these two bound, at first you might find it to be slightly magical. Like, how can this be exactly the same? Like, these are the same. Like, this is multiply every log gradient log term with the same quantity. This is multiplying each gradient log term with a different quantity, which is the value function at each time step. Okay. It turned out they're the same. Okay. Space. So I want to introduce another thought. Suppose I have a function that actually doesn't depend on the action. It only depends on the state. what would happen? So this is where the baseline will show up. So suppose I have a function, let's call it b. It's only a function of the state. And I'm going to multiply by the log. Okay, so the form of the policy gradient so far is some quantity times the grad log. Okay, so one idea is like, what if this is more like the state value function? Okay, there's a reason why we should think about that in a second, but what will happen with this expression? So here the action A is drawn from pi. Okay. So let's work it out. So this is an expectation. For convenience, let's assume that things are finite, so I can write summation, not integral. So I have the baseline times the probability that action is chosen. Times this squared. So I'm running out of space, so I'm going to do what we did last lecture, to plug in the chain rule in calculus into this expression where, if I take gradient with respect to log of some function, I get 1 over the function outside. Okay. So and then I obviously get also the gradient of the policy itself, the policy probability of choosing action as well. Okay, so obviously I do not do the chain rule for another reason, because there's clean cancellation that makes all of us happy. Okay, so what you get at the end is you get the cancellation here. And this quantity doesn't depend on my actions. I can actually pull it up. And I get sum over A what's the value of this? Let me do one more step. So gradient, sum of a gradient, the gradient is a linear operator, so we can whenever you see a sum or average, you can put it outside. Okay. So we can do this, and put the sum here. What do you think the gradient should be?
0.
0, why?
Because the sum is always 1.
Oh, excellent. Okay, so as Michael said, I don't actually care about what policy you use. Whatever policy you use had to sum all the probabilities to 1. So, I'm hiding all the parameters here, but no matter how you change a parameter, this sum of probabilities is constant. Therefore, the gradient is 0. So there's nothing happening there. It's a flat function. As a result, this thing is 0. Okay. So what's the takeaway here? So if I introduce some function, some baseline function that only depend on the state, not the action. The multiplication with the expectation outside will not change the expectation at all. Like, so, you know, if I subtract of any, like if I subtract of any function here, if I subtract any function here from the action value and multiply with the gradient, the expression will remain the same. Okay. So this basically give more space, the A version, the advantage version. Okay. A very natural choice of the baseline function. Looking ahead for the remainder lecture, we'll talk a lot about variance reduction. We may choose some baseline functions without affecting the expectation, like the quantity we would like to estimate, but it will be more favorable in terms of variance reduction. And the quantity we're going to choose, I guess there'll be a dependence on h somewhere. Let me put an h here. Will be the state value function. Okay, so if I plug in, if I subtract the state value function from Q, that basically give us the advantage function. So let me write it out. Okay, so you have seen this from the last lecture, like the last part of last lecture, and this function, not surprisingly, is just Q H minus the state value. Okay, and it's called a state value function because it only depends on the state. And it can be an example of this baseline function v of s. Therefore, if I subtracting off this function, the state dependent only function, the product with the gradient will be 0 when I take expectation. Okay, so these two quantities are exactly the same, but because I'm just adding 0. All right. There's some intuition why this will be a choice of baseline. One idea is, you know, this is really the expectation of the action value. Right, so this is just saying, like, you know, what is the average action values with the action being chosen randomly from the current policy. Okay, so in this expression, you basically like have different choices of A with different probability at each time step. So this is a random variable, even fixing the current state SH. So you might encounter different action values at this time step because you choose different actions. The values can be quite big because it's a sum over a lot of things. Right? It could, like at the beginning, you're summing over H rewards. So the scale of this thing could be quite big, no matter what action you choose. One idea is to subtract off the average from all of these quantities, which turn out to be the state value functions. Right? So if all of these numbers are big, you know, the estimation could be very high variance. You know, one basic intuition from statistics is if you want to estimate something that's large scale, noise come with it is also large. So you might actually have a harder time to get a low variance estimate for this. But if you can shrink them, or you can like subtract off some baseline without changing the expectation, you get a win when you have to estimate them. Okay? So we'll see like, how this will play a role when we have to estimate a gradient. So far, everything here is like in the so-called true gradient, when you actually get to run this infinite many times, like get to roll out infinite many trajectories and take averages. In practice, you probably don't. You probably don't want to do that. Any questions so far? Okay, so all right, so how would you estimate these things? So usually the first thing people try to think of is the so-called unbiased estimate. So that's usually how it's done, at least for supervised learning. Right? So in supervised learning, you also almost never take the full gradient or the true gradient, because that usually involves taking average over the entire data set that might be coming out of different data centers. What you like to do is take a subsample, like take a random subsample, and it would not be the exact true gradient, but it will be an unbiased estimate in the sense that when you take expectation over the randomness of the subsampling, it will be the same thing. It will be the population expected gradient. So this is usually called the Monte Carlo sampling methods. So you will roll out n trajectories. Let's call it tau 1, tau n. So pictorially, you should just think about like, you have the current policy, you want to get a gradient of, an estimate of the gradient written above. What you do is, you interact with the environment, usually you know this as P, that include the reward function and the dynamics of how you transition between states. So you have like tau 1, I guess the theta here, so they include S0, A0, R1, R0. I'm going to put 1 here. And you have tau I all the way to tau n. So you have all these trajectory like this. All right. So so by doing these rollouts, like really n trajectories, it really means like you start at the initial state, drawn randomly from the environment. You use the current policy to interact with the environment and generate a bunch of state action reward triplets until the end that consists of one episode or one trajectory. Sometimes people call this the episodic RL, because you can put an end to an interaction as opposed to the continuing idea of what Drew described. Like you just have one agent that continuously interacted with the world and never end. But here you think about the things happen across episodes. Okay, so by taking some sort of averages, you can already start writing down the sort of unbiased estimate. So if you look at the top one, the top expression for policy gradients, it gives you the most obvious way to get an unbiased estimate. So one estimate you can have will just be hoping law of large numbers working for you and take averages over the total reward you've seen so far. Okay. Okay, so the first one basically is roll it out in full and sum up all the rewards, multiply with all the gradient of the log probabilities, and take average over n trials and episodes. So the paper I mentioned basically argue you doing this already worked pretty well for language models. You can obviously also do the Q version. So at some point you will have at some point trajectory you have SH, AH, the I trajectory, RHI, all the way to the end. I'm going to skip this. So if I want to invoke what's more like the Q version, I will just take the sum, which is like the rewards I experience from there on, right? So I will just take the sum of the rewards and all the future rewards until the end. Okay. That will give you an unbiased estimate for the Q. Okay, so obviously you can do basically the same thing. Right? So this is also, you can also basically take a different formula averages. So nothing super interesting going on here, really just like you roll out the trajectories, you get somewhat fresh estimates of all these quantities, take averages. Okay, so far this is usually referred to as the Monte Carlo sampling methods. So when I think in RL, in reinforcement learning, when people say Monte Carlo, at least in this context, that usually means you're actually getting the estimate after you roll out the full trajectories. Right? So you often involve some sort of sampling of full trajectory. As opposed to your different methods that you can sort of perform update even as the trajectories start happening, as the trajectory is happening. So here, the basic idea is you always like wait to the end, make sure everything is happening properly, gather your data, and take out. So in statistics, there is analogous ideas on Monte Carlo. In the context of RL, however, you can anticipate these quantity, these estimators, to be high variance. So like, suppose like the horizon is super big, you're summing over a large number of random variables, they fluctuate a lot. As you sum up more things, the sum of the random variables fluctuate more and more. And you will anticipate things like the total reward and the estimated action values to also fluctuate. So it will be, and this is like multiplying with the log of the gradient of the log. Okay, so in practice, like you might anticipate these things to be quite high variance, like especially maybe in robotics domain. So there are ideas around how to reduce variance. And it basically went back to something like the third form of the policy gradient, or the basic idea of how to subtract off some baseline that only depends on the state, which doesn't affect the expectation. So you still are moving toward the right target, but the expression favor the estimation, as in it will be introducing a lower variance quantity. Okay. So we'll talk about basically two ideas around this space. So if you take a pause on a moment, like this is sort of where we slightly depart from our original motivation of directly optimizing the policy, like just use the modern machine learning workhorse, SGD, just like run enough GPU hours with gradient computation, you do well. Well, it turns out the value function can come back to be a useful tool for even if you take this gradient-based optimization. Any questions so far? Okay. Okay, so I'm going to talk about what is known as the actor-critic method. There are details and notations, but really, to summarize in one sentence, this is just a way to learn the baseline function. The baseline function is the value function. It's a state value function. The state value function obviously is a function only of the state, and therefore by subtracting this value function from any of the expression, you would not change the expectation. Okay. But in a little bit more details, it's revival of this picture again. So the two parties, one is called the actor, the other is called the critic. But these are just different names for the policy, which is usually, so far in the lecture, is called pi of theta. The critic is usually the value function. We have to learn them, so we'll attach some parameters here. So depends on the context. For different problems, there are different ways to orchestra how you design the underlying functions. For pretty complex problems, like oftentimes these are two neural networks. The policy is some neural network that takes state as input and spit out probability over actions. And the value is just spitting out some real value. But oftentimes they might be two neural networks that share part of the architecture. So maybe the lower layer is actually shared, but the upper layer, they have their own way to output their own format of output. For simpler problem, it's not unusual to have two entirely separate neural networks. Okay. So we'll revisit this picture of having the critic evaluate the current policy, but it would not be the exact same form as before. Like previously, in what we like to call the tabular setting, where the state space is quite small, you can just exactly write down all the values by doing backward induction, by enumerating these Bellman equations. Here you would just do a little bit of gradient update. Okay, I will write down what that means. And then you would do some sort of improvement. Here you will also not be doing the greedy method. Like in the first lecture, in the simpler policy iteration, you would just write down all the action values at the current state, take the max. Here you would just sort of the same idea of conservative policy iteration, you just make a little bit of an improvement by following the gradient step. Okay. So a little bit of details. So here, the improvement, I guess the improvement is this part. We'll do policy gradient, but we'll, instead of the Q version or the reinforced version, we'll try to do the sort of the advantage version. Okay, so we'll replace Q. So the gradient updates will look more like okay. There's some average outside I'm not writing down, like, but you know, essentially I'm basically multiplying the gradient. I guess there's a I'm adding a dot here to indicate this is not part of the gradient operation. I guess nothing here really depends on theta directly. I'm replacing what is multiplying with the gradient of the log with this quantity. Okay? And you can start thinking about why this may look like the advantage version of the policy gradient. So this quantity is sometimes called the temporal difference error. I think by notation, or the method itself usually goes by the letter TD0. So the idea of temporal difference will come up times and times again if you study the literature of reinforcement learning. It's sort of a stark contrast of the Monte Carlo method. So why do we study this object? In this context, in terms of how to update the policy parameters, you would like to sort of introduce the advantage version of the policy gradient, with the idea that by subtracting off the value functions, you are dramatically making these quantities smaller, and therefore you will reduce the variance. Well, it's hard to estimate the advantage. Like, you know, it's kind of hard, right? Like, I don't know. I have some critic that's imperfect. So temporal difference is the idea that I pretend that I have the valid estimates now. Okay? In statistics, that's usually called bootstrapping. Have people heard of this word, bootstrapping? Some nodding. So I have a struggle with this word because I think it came out of some tale in Germany, which mostly is a negative connotation. So what does bootstrapping mean? Like, it's the strap on your boot. I'm not wearing a boot today. You are. So there's a strap behind your boot. The idea of bootstrapping originally means pulling yourself out of some mud, a pool of mud or something, by pulling on the bootstrap. not gonna work. So it's like trying to create something out of nothing. But in statistics, it's usually used as a somewhat positive, it has a positive connotation. Like if you only have a data set, you don't have access to the full distribution. What do? You pretend the data set is the full distribution and draw data from it and pretend that's a pretty good proxy. It's the same idea here. Like you would like to compute the advantage, but you don't have the true state value functions. What you have instead is something provided by the critic. So it's an imperfect proxy. So all you're going to get is some sort of approximation of the advantage function. Okay, so things are random here, so the actions are chosen randomly. So you add, in some trajectory, you end up taking the action a sub h. Okay, in that form, in the advantage version of the policy gradient, you would like to multiply these gradients of the log with the advantage. You don't have that, but if you pretend this phi is a true values, this is exactly, in expectation, this is exactly the advantage. Okay. So the idea of temporal difference is, even though I don't have the true estimate, I don't even have the unbiased estimate, but this is providing me with some signal of what the advantage is. And I immediately use that to update. So instead of waiting until the end of the trajectory, like in Monte Carlo, as soon as I encounter like some delta here, like some advantage here, I can calculate based on the proxy. I do a gradient update. Okay, so I will try to write down the pseudocode, but like that's the idea. Any questions so far? Okay, so the critic is trying to solve some problems. There are different ways to do it, really. Like, the critic what's the critic trying to do is trying to learn the current value function with this policy. So in general, I try to minimize some loss function that looks like expectation of, and the TD error will show up again here. Okay, so notice this term is shown up twice. Okay, so here it was used as a proxy for advantage. Okay, here is used as almost like part of a regression problem. So this term inside is called TD error, temporal difference error. And in expectation, sometimes called the Bellman error. It falls out of the Bellman equations where, if you form the true value function in expectation, like the sum of these should equals this value. Okay? So in expectation, if I have formed perfect value functions, the current reward plus the state value function of the next state should be exactly the value function of my current state. Okay. Obviously, in practice, you would be drawing samples; they won't exactly match. But because it's expectation, they should match exactly. You can sort of use it as a error signal to optimize the parameter phi for the value functions. Okay. So this quantity is used in two different ways, but basically, when you encounter the next step, the critic is basically taking a gradient by optimizing this function. So let me just sketch out what the pseudocode looks like, and then maybe I will keep talking a little bit about the GAE method. So what you do, here's one version of how you do it. So by episode, I really mean trajectory, so pretty much the same thing. So every episode I'm going to do I'm going to do two things. One is the I guess I will also enumerate the time steps. So there are two things happening. One is the critic update. So what you get is write down this quantity. I'm going to define it as the delta H. This TD error, temporal difference error function, quantity is the rewards I encounter at this time step minus plus the estimated value for the next step I encounter minus the current state value. Okay. There's some details, but like basically we'll do a gradient update that looks like some learning rate times the gradient of this. Should be a delta somewhere. Okay, so this is, if we work out the math, this is what the gradient looks like. There's a little bit of detail of why this SH+1 doesn't show up. Part of the reason is this is sort of come out of like the bootstrap way of thinking. You sort of think about like other estimates for other states, for the next state being fixed. You sort of think about those are being fixed and provided to you for now, and you only want to update so that at least the current state value is like making progress in making the square error smaller. Okay. And then there's just the actor update, which is really just applying this gradient estimate. Okay. So I'm hiding some details here, how we brought out the trajectories, but this is all the idea. So this is the basic version of actor-critic methods where you bring back the value function or the critic, so to speak, that guides you to get a low variance estimate. And to contrast with the Monte Carlo methods, you don't actually wait for the end of the trajectory to update. You can actually perform update every time step. Yeah, so you can sort of immediately perform a small update. Yes.
Is the parameter update for the critic supposed to be phi minus?
So it's not, because it was minus, but because there's minus before the v, I think it worked out as plus.
So is that not to minimize the loss?
No, let me say it again. So if you compute gradient, so treat this one as a constant, by the way. You apply chain rule, this will come out as like 2 times this. There's a negative here. So you will negative the gradient. So negative twice, you get plus. So we do want to minimize loss. That's a good observation. Okay, so this is sort of a low variance technique, and you can see that in many ways. One way to see it is you don't actually wait for the full trajectory to happen. You kind of make small incremental update as soon as you see a new observation. As soon as you see like a new state action reward triplet. Okay. You're moving slowly, but it won't be an unbiased update in the same way as the Monte Carlo because you're reusing current estimate of other state values, and they're not perfect. So you will introduce some bias in some ways. Okay. So I want to spend a few minutes sort of talking about a middle ground between these two worlds, right? Like these two seems a little bit extreme. One is like wait for everything to happen first, then update. You have lots of variance, maybe no bias. Here is like as soon as something happened, you do a small tiny update. And you're going to use the critic to the value function to improve the variance. So there's a middle ground. Basically call it JE. Oops. So I'll generalize okay. So we're short in time, so here's the idea pictorially. So what's going on with the rollout? I'm going to draw a picture here again. So you have a pi theta, which induce some trajectory distribution p theta. And, you know, it's kind of like pushing a button and generate a sequence. And what you get, well, you know, laboriously, you have state, action, and reward. I'm going to skip some of this thing. And then you have next reward. 2. At the end of the day, you have RH minus 1. Okay. That's sort of the rewards are really the more relevant quantities when we do the estimation. Okay, so what's the actual critic doing, right? So, or at least the so-called TD0 type of method doing. Well, at this time step, I'm going to relate. At every time step, I'm also forming a value estimate. And so on. And you know, this thing, the last one is not interesting because it's the terminal state. This is 0. The last state, there's no more reward. Okay. So the TD0, the way you do this sort of temporal difference update is relate these quantities. Right? So, like, for example, these 3 and so on, right? So this triangle will give you something like delta H equals RH plus the next state So what's the algorithm doing above, right? You know, as soon as you hit one more step, you observe a triangle like this. And therefore you can calculate this delta, this sort of the temporal difference error. And that will be useful in both updating the policy because it's the proxy for advantage. So you can actually start doing the advantage version of policy gradient. Also, it's related to the square loss objective the Bellman error objective that the critic cares about, and you can use it to update. Okay, so it's a little myopic because it's very much taking a local view as soon as you take one step. But you know, you can start writing down sort of like multi-step version of this. Right. So instead of using the single step delta as a proxy for advantage, you know, you can maybe do something like n step. Right, so instead of just look ahead one step, gather the reward and do update, maybe you move a few more steps, you know, be a little bit patient and like see a bit more signals. But don't go all the way to the end, maybe like, and use that to update. Okay, so one alternative will be at time step h, I'm gonna roll out a few steps. Right? And then at some point I would decide to stop because if I keep going, it would never end. I would just add up the estimated state from then on minus my initial state that started out with time step h. Okay, so this is not the final quantity we'll use, but this is also a reasonable thing. This is sometimes called a multi-step methods. Right? So the so-called TD0 method is sort of like take one step, calculate the difference, just like use Bellman equation once, take a difference. Here you take a few more steps, n steps, and take a difference. So this is another estimate of what is the advantage that the action A is responsible for if I look ahead a few more time steps. Okay, so this is also something you can do, but not exactly what generalized advantage estimation will be doing. It's sort of a parametric form of this multi-step idea. So instead, a different way to estimate the advantage will be looking like this. Let me draw a line here. So what's called the generalized advantage estimation usually take an estimator that looks like the following. Take what you would have gotten by taking one step, delta H. But you look ahead a little bit. You look at the next step. Okay, so that would be the TD error in the next step. You roll out one more step, you gather this. And you keep going. Right, so and eventually you hit the final state. Okay, so it's sort of a parametric idea. I guess it comes with a parameter lambda. A parametric form of, you know, implementing the multi-step version. I guess the multi-step version is a bit more, it's less flexible, like you have to stop at some time step n. This is just sort of like incorporating all future rewards into consideration. And you can also do this recursively, so you don't actually need to wait until the end to actually get this estimate. You can actually do the update without seeing the whole sequence. The summation will work out. The summation is sometimes called the eligibility trace. It's not too important for now. But this is just an effective interpolation between the TD0 method, the usual basic actual credit method that use a single time step to update, and the multi-color method that wait for the entire trajectories and only do stuff at the end. Right? So this is sort of like putting weights on future, right? So if you convince yourself a little bit, right, like, you know, What if I set lambda to be 0? What algorithm is this? What estimate would that be? You point out.
This up to 0.
TD0. This is sort of like the TD0. And how do I recover the Monte Carlo estimate? Lambda equals 1. Okay, so typically you will think this is like, for this, you know, the bias is small, but the variance is high. And this is the exact opposite. Oh, sorry. Bias is high. Where here, you know, you have unbiased estimate. The variance tend to be high. Okay. And this generalized advantage estimation sort of allow you to choose a place to be in between these two extreme worlds. And it turns out to be a single parameter that you can tune. So it's a pretty cool way to do things in practice. I think I'm out of time, but this is exactly the topics I want to cover. We'll have one more lecture on policy gradient next week. It will be covered either by me or Gokul. Next lecture will be really fun. It's about an algorithm called the natural policy gradient. Okay, see you then.